let's just jump right into it, right? So what is this about? After this session, what I hope is you have sort of a mental model to be able to relate between performance and scalability, and sort of start having somewhat data-driven approach to understanding the systems that you are building, right? And we'll talk. I think once you see that, you'll understand why it is very important to understand that, right? Because if you don't, then you will be ending up, sort of spending time in areas where it's not really needed. Okay, so to get into it, right? So there is a tunnel. Okay, now when we are trying to understand performance and scalability, this metaphor will come in very useful, right? So this is a very call it a crude representation of a tunnel, right? So imagine you're driving your car. In this case, it happens to be a Ferrari, and you're driving it through that tunnel. The performance question is, how much time does it take you to go through the tunnel, right? And that is a relevant question because that determines how fast you can go and how fast you can sort of reach your destination, which perhaps lies on the other side, right? The performance question, the answer to it is measured in seconds. So maybe it will take you 10 seconds, maybe it will take you 30 seconds, but it is a time measure, right? How will you increase the performance? Either you reduce the length of the tunnel, which the theory of relativity can perhaps be used to do that, but then you can increase the speed of car, right? So if you increase the speed of car, you will get to your destination much faster. Okay, so the key thing to understand here is that performance is measured in seconds. Okay, now let's talk about scalability, right? The scale question is a different one. The scale question is a traffic question, right? How much traffic can the tunnel handle, right? So it is a bulk question. It is not about one single car, but at a given point of time, how many cars per second can the tunnel support, right? When we say cars per second, it is, you can think about it as how many cars per second are emerging out of the tunnel. Okay, so that determines the amount of traffic that it can handle. If you throw traffic, throw more traffic at it, then it will just slow it down to its acceptable speed, right? Now, in order to increase the scale, the key thing to observe is reducing the length of the tunnel doesn't help. Okay, so let that sink in. I mean, it doesn't matter whether the tunnel is 1 kilometer long or the tunnel is 100 meters long, right? The amount of traffic that can come out of the tunnel at any given point of time is indeterminate by is just not based on the sort of length of the tunnel, right? Now, how do you increase the traffic? You increase the traffic by increasing the width of the tunnel, so perhaps more than one car can go at the same time, and then increase the speed of each car. There is another keyword there, right? Each car. If instead of a Ferrari there is a Volkswagen minivan over there, then what will happen, right? I mean, the speed of the tunnel will still, or rather the scale in which what we mean is the number of cars emerging out of the tunnel will still be the same, right? Because there is queuing and, everybody is queued up behind it. Okay. So I hope that, gives you a sense to understand, right? And what is the key thing to understand here? The key thing to understand is that scale is not measured in seconds. While performance is measured in seconds, scale is measured in this case, cars per second, right? Now, if we go to a more technical thing, right? Performance is measured as response times, right? What is the response time? Response time is the total time taken by a request to be processed and the result to be returned. Okay. Scale is measured in throughput, right? And throughput is different from performance and response time, right? Throughput is a per second measure. How many requests per second can my system support sustainably? When we say sustainably, it means that it is sort of in a steady state. It does not degrade over a period of time, right? The response times don't get really bad, are still within an acceptable range, and so on and so forth, right? Now, how much is sustainable depends on your system. For some system, you will have to sustain for, let's say, an hour. For other system, it might be 4 days. For some systems, it might be just a peak load of 10 minutes. Okay. So I hope that drives the difference between performance and scale clear, right? Let's think about additiveness, right? How does performance add or subtract over time, right? So if you have two systems, we have the first system which has a performance of X seconds and the second system which has a performance of Y seconds. the overall performance of this combined system is X plus Y. Right now, going back to our car and tunnel metaphor, if a car takes X seconds to go through this and there is another tunnel to cross, it will take X plus Y seconds. Same with request. If one request takes X seconds to go through, let's say, your web server layer and Y seconds to go through your app server layer, then the total time taken by that request would be X plus Y. Okay. Now, the funny thing, it is bad, right? It is bad because your performance degrades as soon as you add more systems. Your performance also degrades when you add two systems, or rather your scale also degrades, or your throughput also degrades when you add two systems, but it degrades in a different way, right? So your throughput is only as bad as the worst system that you have in series, right? So, if I have a system X per second and I have a system which supports Y throughput per second, the one of them will become a bottleneck, and which one will become is the one which supports less throughput, right? You can imagine it again in terms of Bangalore traffic, right? If you are going through the traffic, there are these junctions, and those junctions become the controlling factor, right? It's not the roads. You can go zip through the roads very quickly, but whenever you hit a traffic light, it is the traffic light which is controlling the throughput. Okay, so whatever is slower, the speed of the whole system becomes the speed of that, right? So for systems in series, performance gets worse. The scale is only that also gets worse, but it is only as bad as the worst one. Okay. Now, if you two systems in parallel, right? I mean, think of it as there are two routes that you can take. You can go through this system, which will take X seconds. You can go through Y, right? So there are sort of two roads to take to the same destination. Now, depending on which road you take, the other one does not affect you at all. But let's say you are making multiple journeys and you choose between the two. So, it will be sort of an average of the two, right? In case of scale, the scale doubles, right? I mean, if there are two routes to go to the same destination, half of the people can follow one, or half, or perhaps more in some cases, but other half can follow the other, and the total amount of throughput that can be supported is a sum of the two. Okay. Now, in this case, the performance does not increase by a lot, but in this case, because throughput is additive, as soon as you add parallelism, the overall throughput of the system scales by a lot. Okay. Now that is the key thing to understand as we go on to the next one. By the way, one thing I have is that instead of waiting for questions at the end, if you guys have any questions, just feel free to type those in. Okay. So type in the questions at the time that you have them, just in time, and then we'll answer that. We'll take a break and answer that. Right. So just put down your questions right away if you have any of them. Now, if we think about those two natures, right? I mean, if I were to increase performance, right? The way to increase performance is, my cars must go faster, right? So I have to reduce the time taken at each step, okay? Or I can perform some steps in parallel, right? We are not saying we should add another system, but we are just saying that, break it down, and instead of doing it at one after the other, do it in parallel, right? If you want to increase scale, then of course reduced time taken at each step should increase the scale, right? But you have to do it at each step, right? I mean, because scale is determined by the minimum of all of the different tunnels that are there in series. Or you can add parallelism. You can increase system capacity to provide multiple paths to the same destination. Okay. Now the interesting thing is, the reduced time taken at each step is often what we think about when we are to increase the scale, right? I mean, as developers, the requirements we hear is, I want to support 100 concurrent users, right? Now, in order to support 100 concurrent users, performance can only be improved by so much, right? Unless we understand scale and unless we understand bottlenecks, we will not be able to get to a throughput of 100 per second if we are just focusing all of our attention on performance, right? Because it is the performance of each and every part of the system which determines the scale. In fact, the worst of them is what determines scale. So there is an interesting law, right? It's called Little's law. Okay. What does it say? It says that the average throughput of the system is equal to the total number of requests that are there in a system at a given point of time, right? So again, in our car and tunnel example, the total number of cars which are in the tunnel, not the cars which are outside the tunnel, the cars which are in the tunnel, right? So in some sense, that gives us, what is the parallelism? How many parallel requests at a given point of time can you support? Okay, and then divided by the average time to serve a request, right? So it's sort of a very, very intuitive thing, and for a long period of time, people thought that it is a given thing, right? You didn't even need a proof for it, but proofs were provided later. But then it connects the three things that we care about in a very, very clear mathematical way, right? Which is average throughput is parallelism, the number of parallel routes that you have, divided by performance. Now it's sort of slightly different because good performance means smaller average response times, right? So it's not really divided by performance, it's multiplied by performance, but you get the idea, right? That higher performance, higher parallelism means better throughput. Okay. Now the other interesting thing is that this implies that it is a steady state, right? A steady state means that there is no queuing in the system. It does not apply during a ramp up phase or a ramp down phase. Right? It is when the system is fully utilized, right, and is working in a steady state. Okay, so let's see if we have any questions so far.
We don't have any questions as of now, Anshuman.
Okay, guys, if you have questions, just feel free to put them in. We'll take a look at that towards the end. Okay. So let's look at a working example, right? So what we talked about so far was essentially math and theory, right? And very, very intuitive math and theory, right? But when we apply it, it's interesting that because we don't have that mental model in our minds, we often get misled, right? We often try to focus too much on the response time and optimize it, and don't understand why the performance is not getting better. Because we don't have that mental model, right? Or rather, throughput is getting better because we don't have the mental model. We don't understand that, it is not just performance of one piece. It is the scale of the overall piece which matters, right? If you have to achieve high throughputs. So let's take this simple example, right? This is a simple 3-tier application, right? Assume this is your incoming network, right? Assume you have your system server which has 2 CPUs and it has 4 GB of memory. Okay, assume this is the network connection between your server and the database, right? And of course the database will have its own memory, its own CPUs, but for sake of simplicity, assume that the throughput that the database can support is 20 per second. Okay, so there is a network, incoming network, so requests originate here, they go through the network, they come to the server. On the server, the CPU will exercise it or process the request. There will be some memory which will be used for keeping cached objects or intermediate objects, etc. It will make DB calls. So you will use the network between the server and the database. And then finally, on the database, assume that database can support 20 per second, right? 20 requests per second. Okay. Now, once we go down, right, what we realize is, and suppose this is one request which is coming, right, and these are all made up numbers, right, so the actual numbers don't matter, but one request utilizes 5% of the network bandwidth that you have. Okay, 5% in this case means about perhaps 20 or 1/20th of MB per second, right? So it uses only 5%. 2 CPUs, so it uses 20%, and 2 CPUs means you basically have 200% CPUs available. So it is using only 20%, which means about 1/10 of available CPU power. It uses 20% of 4 GB memory, right? So about 1/5. It uses 10% of the network connectivity between the system and the database, right? And 25% of the database throughput is used. Okay. Now, if you know this, right, and you should be able to compute what would be the scale of this system, right? And we are talking about theoretical steady state, right? So let's try to do that. Okay. So 5% means you can support 20 such requests at the same time, right? So the parallelism which this layer can afford is about 20 per second. The parallelism which this can afford is 10, right? Why is it 10? Because 20% is only one CPU, 200% is total. So 20% is like 200% is 10 times 20%, right? So it can support 10 requests at the same time, or parallelism of 10, not 10 requests, but parallelism of 10. This can support 5 because we are using 20% of the memory, 800 MBs, which means 5 total can 5 more requests can happen, 4 more requests can happen, so a total of 5. Same thing here, 10, and because this is utilizing 25% of the DB, it means we can support 4 more, right? Now, let's say this the response time taken for this one request to be processed is 0.5 seconds. Okay, so half a second. Now, let's look at these numbers for a while, right? And I know you guys can't interact and respond, but just think in your mind, what would be the total throughput of this system, right? I mean, if somebody gave you this numerical problem and asked that, Mr. Developer, tell me how many requests per second or how many concurrent users can you support if these are the characteristics, okay? So think about it for a bit. I will actually reveal the answers in a moment. And if you have any other questions, use this to also post in the questions. Okay, so now let's get into it, right? So what happens, right? We talked about that when systems are in cities, when systems are connected in cities, then the parallelism is only equal to the worst of them, right? So even while this supports 20 per second, this supports 10 per second, and so on and so forth, the actual parallelism will be determined by the database, because you're getting bottlenecked on the database because you're using a lot of it. So it means that everything else will lie unutilized, but then your whole throughput is determined by this, right? Now, if you do that, this red one becomes the bottleneck. Hence, our expected parallelism is only 4. If you go back to the Little's law, the total response time is 1 second. So if you go back to the Little's law, the total response time is 0.5 seconds, right? So if you remember, it was parallelism divided by response time. So our average throughput will be 4 divided by 0.5, which is 8 per second, right? Which is kind of very intuitive that if my database is the bottleneck, it can support 4 per second. Every second we are firing 2 requests. So, it total becomes 8 per second.
So Anshu, we had an answer from Om that was 4 per second.
Yeah, correct. Perfect answer. Okay. Now, if we go a little bit beyond, right? So let's say, we optimized our query by reindexing. Okay. We optimized our query, we reindexed it, we reduced the total number of queries to 10 with average response time of 100 milliseconds, which means for every request, you are utilizing about 1 second of the database, right? So 10 total requests and 100 milliseconds. Now again, those numbers won't add up, but just for the reasoning, assume that because the network traffic has decreased, instead of 10%, it is now using only 5%. Here, instead of using 25% of the database, it goes to use 5%, right? So we have a 5 times improvement on that because of indexing that we achieved on the DB, right? Now this is using only 5% and we have 5 times improvement. You know what this number will change to? So it will change to 5 times of 4 because we have more parallelism. So it will essentially become 20, right? This also improved. So this will again become 20. Now in this improved scheme of things, if you were to calculate the throughput once again, this is now constrained by the memory usage, right? So the memory usage is now determining the overall throughput of the system. So, instead of 4, which was earlier coming from the database, this will become 5 and 0.5 seconds, which means 5 divided by 0.5. So that is a throughput of total 10 seconds. Okay. Now, let's say we optimize the memory usage, right? Reduce the overhead of objects which were created. So, and we're able to increase it from 10% to, 5%, or rather decrease it. So it goes to 22 times of the earlier parallelism, so 20. Now, but, the overall performance does not increase to double, right? The overall performance is now bottlenecked by the CPU, right? Because the CPU can only support 10 per second. And so it overall becomes 10 per second. And then the final number is 20. Right. So what is happening, right? So what you have to understand, in your mind is that if you double the performance of the system, the throughput doesn't double, right? It just settles on the next bottleneck, which can be, which might be the same, right? I mean, which means that even if you increase the performance of one piece of the system by 10-fold, the overall performance or the overall throughput just does not increase at all, right? Because it gets bottlenecked at a different place. Okay. So, CPU usage, we cannot optimize. So we add another server and, sort of things go on like this. Okay. Now, if you were to look at it in terms of graph, right? I mean, these are performance improvement. So first time we tested, we find that, we are firing too many queries which are slow. So, our database becomes the bottleneck. So while we are increasing load, the throughput does not increase at all, right? Then we prove some critical performance. We find that, that problem is solved. So throughput increases until a specific capacity. After that, it goes, and, in our example, it was at 10. So it goes and stabilizes at another number because now there is another bottleneck which is coming into the picture, right? And then we reduce the objects, so we reduce the memory bottleneck, but now we identify that, there is something else which is becoming bottleneck.
So Anshu, we have a question. Sorry to interrupt you. This question is from Mayank. So his question is how to calculate those initial percentage of the server.
So let me get back to that, right? So I will answer that in a moment, right? But just, there is one main point which I wanted to make here, right? Which is that often enough, and, this has happened innumerable number of times, right? That people would come and say, this was working great on my, laptop, and I put it up in the in AWS environment, let's say, right? And I'm not getting the throughput I need, right? I'm just getting 10 let's say requests per second, a throughput of 10. My performance is great. My everything, returns back in, my every response returns in 100 milliseconds, but I'm just getting a throughput of 10. And, really what we need is a throughput of 100. What can I do, right? So you have to understand that, it is parallelism, right? And, I mean, if only I had a penny for every time, we made this mistake, right? But you have to understand the parallelism across your system. And, often you find that you're not even using parallelism at the server, right? Which means that you have a single worker which is there and, trying to serve all the requests, which just reduces the parallelism drastically, right? So it is a very, very dumb problem, but it is a very, very common problem. As soon as on the day that you go to production, you realize performance is not great. The first thing to check is how much parallelism that you have on the server, right? And, you can use, you can specify it, hard code that limit, have 20 workers, or you can use something like an asynchronous worker. But the main idea is increase the number of workers and test until there is no benefit in this game, right? And that is the other part, right? Test. And that is sort of also the answer to man. You will have to test it out, right? You will have to test it out by actually running the system, okay? Because I mean, what this deals about, and Fahad and Guru already covered that part earlier, right? That there is no alternative to performance testing, right? But what this presentation talks about is that after testing, after you have that data, right? You have to really understand and think about it by assigning these numbers to these different parts of the system and figuring out that which is the system piece which is actually bottlenecking on, right? Because often enough we go and developers, right? We know that we have access to code, right? So the first thing we jump into is how do we improve a code performance, right? But often throughput is not a coding problem. It is a parallelism problem. It is a deployment issue, right? So if you have to understand throughput, you have to understand your deployment. You have to understand all the different systems which are making up your application. And only then you will be able to understand throughput. And only once you understand throughput, you will be able to increase it, right? Because what you don't want is to keep optimizing and spend all of your time on part of a system which doesn't even matter, right? Because there is some other part which has a much lower throughput than what we have. Okay, so that's all, guys. That's all I had. Mayank, I hope I answered your question. If not, please feel free to give a follow up on that. But
Anshu, we have a question from Himanshu. So his question is how to find the independent entries throughput.
How to find the
independent entries throughput.
How to find the independent entries throughput. So it's simple, right? I mean, you basically have to test it independently, right? So now, I mean, that said, most of the people don't go through that. Why do they not go through that? They don't go through that because, really your throughput is determined by the slowest one, right? So what you do is you just keep increasing the load over here and you will find out that one of them becomes fully utilized, right? My memory usage is 100%, my CPU usage is 200%, my network is fully utilized, or my database CPU usage or memory usage or whatever is the bottleneck, that becomes 100%, right? It's usually not 100%, it will go to 80%, right? Because rest is used by the operating system, right? So you keep on increasing the load, and as you keep increasing the load, you identify that, where the bottleneck is, right? So you really don't need these numbers to make these decisions, because the decision is basically, I want to improve my throughput. Let's find out where the bottleneck is. Let's fix that bottleneck and let's improve it further, right? But that said, these numbers you can calculate roughly, and the way you calculate these numbers roughly is, at your, let's say, you have the full throughput, right? You have 100 requests per second which is coming through, right? How much is my CPU utilized? How much is my memory utilized? If my memory is only utilized 50%, then a rough check says, maybe I can double up the throughput. Right? It won't go to a double up, but maybe I can, right? So that sort of determines that what is the residual capacity that I have at any part of the system, and what is the usage currently, and that determines that if I'm using 50% of it to support 10 requests per second, the other 50% can be used to support another 10 requests per second, right? So the max throughput, perhaps it can support 20. But that is theoretical. The real number will only be shown once you actually go ahead and test it out. I hope you guys get it. I hope you guys will use this kind of call it slightly mathematical modeling to understand the system performance and understand where you should focus your effort, right? Because that is very, very important. If you have 20 systems and this was a 3-tier system, right? Imagine a cloud native architecture. So if you have multiple systems interacting, external system calls, etc., you have to understand the throughput of each one of them and how does it all add to them. Okay.